being here, and thank the organizers for inviting me here. So I am going to talk to you about the effects of extreme conditions on enzymes. And as Harrison said, I'm going to be, the work I'm going to show you is done using molecular dynamics simulations. So I just also wanted to start this off with, there's one kind of overriding question that I'm not going to exactly address directly, but one might be thinking about this. And that is, why are enzymes proteins? I mean, why aren't they other things like nucleic acids? And so also, part of what I'm going to be addressing is, are proteins just scaffolds that hold the active site, or do we have to think something more about what they are about? Sort of the protein matrix that holds the active site. Okay, as Harrison said, one of the things that I'm interested in is extremophiles. And because, of course, many, there have been, over and over again, people are finding organisms that live in extreme conditions. And in particular, people have, this is something from Trends in Microbiology, where they talk about what are the limiting conditions of life. And so this is actually what are the most extreme conditions that people have found different bacteria or other microbes. And so this is pressure versus temperature. Actually, this is salinity, but we'll ignore that for now. I'm going to concentrate on temperature and pressure. And there's actually this range, it's 120 megapascal, which is basically 1,000 times atmospheric pressure, and temperatures from 0 to over 100. So actually, just looking at this, you can see that we're finding life over a huge range of extremes. And these pressures around 1,000 atmospheres correspond to the deepest parts of the ocean. And in the cold, deep sea trenches, in the hot, deep sea hydrothermal vents. And just as a summary, the maximum growth temperature that they have found for it's actually archaea, is 100 degrees Celsius, which is actually over boiling at atmospheric pressure. And the maximum growth pressure is over 1,000 bar. But the thing about this chart is based on where people have found life. And what we're interested in understanding is, can we predict where it could exist without actually finding organisms there? Okay, extremophiles are organisms that live at extreme conditions. The interesting thing about extremophiles is these are actually higher organisms, but at a cellular level, whether it's higher organisms or bacteria, they pretty much look like cells from mesophiles, things that live at the surface under normal conditions. Not only do the cells look pretty much like normal organisms, but their proteins. Now, their proteins have to work in order for these cells to work, but they look pretty much like normal proteins. So of course, there are some differences, and we want to understand what those differences are. Okay, so what we've been asking the question is how, if you find basically the same proteins in extremophiles and mesophiles, so how do homologous enzymes from a mesophile and extremophile adapt so that they can exist in these conditions? And there's a hypothesis, which people call the corresponding states hypothesis, sort of like the PChem corresponding states. And the idea, so I'll explain it first for organisms that live at different temperatures. So if you have, my colors have gone wacko, but thermophiles are organisms that live at high temperatures, mesophiles at normal temperatures and psychrophiles at cold temperatures. And the idea is that if you look at enzymes from these kinds of different kinds of organisms, this axis here is activity, this is temperature. The activity is going to be at a maximum near the growth temperature of the organism that it comes from. That sounds logical, okay? So this is maximum activity, hot, medium, and cold. There's also another aspect to this. So for an enzyme to work, it has to be stable. And if you look at the melting temperature of these enzymes, it's higher for the thermophile than the mesophile and the psychrophile. That also makes sense. But there's also a phenomena called cold unfolding. And the place where this crosses zero is where it unfolds. Actually, the cold unfolding temperature is hotter than that of the thermophile. For a psychrophile is higher than that of a thermophile. So it's backwards than what you might expect. And the reason is that in order to become thermophilic, you have to be more stable. But actually, to become psychrophilic, you have to become less stable, because the problem that happens when you go to colder temperatures, things become more rigid. And so they are less stable so that they can be more flexible at low temperatures. I mean, if that wasn't the case, if stability was the only thing that was important, everything should be stable. I mean, why should you want an unstable program? The reason you want to is you need the flexibility. And so there should be similar stability and flexibility at the corresponding states. There's also the idea of looking at the growth pressures, things from the sea level all the way down to the bottom of the ocean. And here I have a comparison of a mesophile versus a piezophile. The mesophile is E. coli, and this piezophile is Moritella profunda. I'm just going to call it MP and EC just for brevity. And what we have here is, it sort of seems to go along with this corresponding states activity idea, in that the mesophile, the activity goes down with pressure. The piezophile, it actually goes up with pressure, and then it goes back down. And so what we've been doing the past several years is trying to understand what gives rise to each of those things. There's also a very puzzling thing, or seemingly puzzling thing. If you look at the unfolding pressure, because pressure also unfolds proteins, is the unfolding pressure of the piezophile, the high pressure organism, is at about 0.7 kilobars, whereas that of E. coli is much higher. So it is more stable to pressure unfolding. Why does that happen? Well, actually, this particular piezophile lives at 0.25 kilobar. So it actually doesn't care that it unfolds at 0.7 bar because kilobar, sorry, because it never gets there. So, okay, so we wanted to look at this question at a molecular level. Oh, yeah, so I made these slides up for a Tuesday night lecture, and I just sort of wanted to point out, okay, we all have a good intuition about what happens at different temperatures. If we start at normal temperatures, if we cool it, these are gummy bears, by the way, which are kind of flexible gummy candies. If you cool it, they get hard. If you heat them up, they melt. That's actually what happens with a protein. At normal temperatures, a protein exhibits thermal or Brownian motion. If you cool it, there's less thermal motion. If you heat it up, if you heat it enough, you break the hydrogen bonds and you melt the thing. We have less of an intuition, though, about what happens at different pressures. again, and this is actually, I stole this from the internet, from YouTube. And so somebody took a giant gummy bear and they put it in a hydraulic press, the hydraulic press channel. I mean, this guy puts everything in hydraulic presses. But when you take this giant gummy bear and you put it in a hydraulic press, the first thing that happens to it is you sort of compress it. But if you put it under high enough pressure, 250 atmospheres, it just squishes and falls apart. That's actually sort of what happens to proteins. So proteins are actually compressible because they have holes inside of them. They're sort of like a sponge. And if you press on them, this is actually a snapshot from a simulation at 600 atmospheres. You compress it at first. But if you keep on pressing on it, you actually unfold the protein. You squash it, and it becomes unfolded. I pointed this out also in my other slides. But you might notice that actually, that in the beginning, what you're doing by compressing it, you're making it more rigid, which is sort of like cooling it. And then you press on it some more, and it's sort of like melting it because it makes it more flexible. Oh, let's see, where am I? Okay, this is a horrible slide I made up this morning, which, yeah, so it's kind of horrible, not very pretty. So this sort of summarizes some things that we have found out about effects of temperature and pressure and some of the adaptations to temperatures and pressure. So one of the things is that temperature, what it does is it affects hydrogen bonds. Okay, so as you increase the temperature, and this is the number of hydrogen bonds for this particular protein, DHFR, between 100 and 108. So as you increase the temperature, the number of hydrogen bonds goes down, which you can imagine you have thermal energy to break the bonds. The other thing is if you compare the mesophile with the piezophile, the number of hydrogen bonds is greater in the mesophile. So why should you have more hydrogen bonds? Well, actually, I've been talking about Moritella as a piezophile, but it's actually a psychropiezophile. So it's something that lives in the cold, deep ocean. So it lives at 279 Kelvin. Whereas E. coli growth temperature is about 37, about body temperature. So E. coli DHFR has to have more hydrogen bonds because it needs to live at a higher temperature than the Moritella. There's not I didn't have a really good measure for the cavity size on this, like in my notes, but my computer. But this is, okay, this is pressure, and this is the number of water molecules that are inside the protein. So you really can't see, it's not a good measure of cavity size, so you can't, doesn't really show the effect of pressure on cavities. But the thing that I wanted to point out is the thing is that for the Moritella, you can fit more water inside the protein. So that would say that the cavities are bigger. So it's bigger in Moritella than E. coli. And so you might think of that as an adaptation for high pressure. Okay? And so this is a slide I also showed on Tuesday. So adaptations for temperature and pressure. If you think of a mesophile, if you want to become a thermophile, the proteins need more hydrogen bonds. Proteins from a psychrophile need fewer hydrogen bonds so they can be flexible. And if you think of, so this is growth temperature, growth pressure going down from, say, sea level. As you go deeper, let me start over here. Piezothermophile is something that likes high pressure and heat. So that would be, say, like next to a hydrothermal vent. So it needs more hydrogen bonds because of the heat, and we would think it needs bigger cavities. An adaptation, on the other hand, for being a piezocyclophile, so this would be something like in the ocean trenches, like the Mariana Trench. That's a high pressure but cold environment. And so in order to do that, you accomplish that, you would say, okay, fewer hydrogen bonds to be flexible and bigger cavities. But actually, when you start thinking about this, like what's it going to do if you don't have very many hydrogen bonds and you have these big holes in it? It's going to be really unstable. So that's sort of a limit, because you can only you cannot remove an infinite amount of hydrogen bonds. You can't keep on making more, because otherwise it just doesn't fold if you don't have any hydrogen bonds. You also can't make huge holes in the protein, because then it's not compact enough to stay together. So this is kind of the most unstable. But because in the piezothermophile, you're doing two opposing things. You're adding more hydrogen bonds, but you're trying to create more cavities. So you can probably balance it so you can actually go either deeper or hotter. And a thing I didn't talk about on Tuesday is actually the direction of evolution matters. Whether you go around like this or you go around like this, that's going to make a difference in the type of adaptation you see. And I'm also, just for your information, I'm sort of thinking that maybe life evolved from a hot, deep, hot surface across over here to cold, and that these piezocyclophiles actually came from cyclophiles. Okay, so this is another sort of complicated slide. I still haven't figured out how to really talk about this, but it's about stressors and the direction of evolution. Okay, so I just said there are two things that enzyme needs. It needs to be stable, and yet it needs to be flexible. But I think that the worst consequence you can have on a protein is to unfold it. And so unfolding is bad. So the stability is the most important thing. So temperature, or I guess unfolding, would be the highest stressor. If you lose flexibility, that's not good. That's what I've been saying. But it's not so bad as completely unfolding a protein. Probably a protein that is a little bit too rigid is just inefficient. And you can make up for inefficiencies by, one thing, just slowing down your metabolism. Maybe this becomes slow growing, which seems to happen in the cold. So high temperature is, I think, a greater stressor, because you have to worry about breaking hydrogen bonds. So it's a greater stressor than either low temperature or high pressure, because this is dealing with unfolding the protein. Low temperature or high pressure, until you get into the really high pressures, just make more inefficient enzymes. And then the other point I wanted to make is that if you're evolving towards a high temperature or very high pressures, the tendency is to add some interactions, few key interactions to prevent unfolding. So the changes, the mutations you get, have to keep it from unfolding. That's important because you don't want the protein to unfold. However, if you're evolving away from the stressor, like towards low temperatures or low pressures, actually what tends to happen is you just lose interactions randomly. Because as you go away from the high stress, you just make an inefficient enzyme. You don't completely destroy the enzyme. So you can make it a little bit better, just lots of ways. And so there's more of a tendency that you have lots random changes all over the place if evolving towards a low stress environment. Okay, now I'm going to talk about, I'm running out of time, some specific adaptations that we have seen between this E. coli DHFR and MPDHFR. So this, again, is what we call mesophilic, and this is psychrophilic. And so the two significant mutations we've seen, so there's a loss of a hydrogen bond. So in E. coli, there's a hydrogen bond between ASP69 or 71. It goes away in Moritella. It doesn't matter. We think this thing keeps it from melting, okay? There's another hydrogen bond. This one's kind of strange. It's between ASP27 and the backbone of residue 113. And in E. coli, it's 100% occupied. And in Moritella, it's only 10% occupied. So when I say, fewer hydrogen bonds, I also mean weaker hydrogen bonds. So this is a weak hydrogen bond. And again, these are more or stronger hydrogen bonds make you work better on high temperatures. So we think that these are things that have helped the adaptation towards cold by just being, one is it disappears or the other is it gets very weak. The interesting thing, though, is this same glutamic, aspartic to glutamic acid also seems to be a pressure adaptation, but we think it's an accidental one. So I'm going to show you in a second, is that the presence of aspartate, it corresponds to the decay in the pressure activity, whereas glutamic acid increases. So actually, there is our rationale for this is that this aspartic acid, it forms a very rigid hydrogen bond, and glutamic acid, which just differs from aspartic acid by 1 carbon, is more flexible. And this actually allows, there's a hydrogen bond between this helix and this loop, which seems to be important. If you have this rigid connection, it breaks. Okay, so why did I say an incidental pressure adaptation? Because all the other sequences of piezophilic bacteria from other genuses do not have this mutation. So it's not a necessary adaptation, it just happens to work. Yeah, so here actually, here I show you is that this is wild type E. coli. If you make that mutation, now this mutation is just really literally changing this to this, which is just adding 1 carbon out of the whole protein. And what it does is it makes the activity increase with pressure rather than decrease with pressure. And this has been shown experimentally. And this is not near the active site. And so it's like, that's why we think it might be this coupling, the fact that it's more flexible. Yeah, maybe. And I guess the other thing, because this is found, most DHFRs have this mutation. Have the aspartic acid. It's not that E. coli evolved to be at lower pressures. It just is. It's something that it just happens that that's something that makes it work poorly at high pressures. And there are other ways to fix it. this is one way that Moritella chose to fix it, but you could use other ways. So actually, I said one of the things we're trying to do is trying to see that this is that curve I showed you in the beginning with the relative activity versus pressure, E. coli versus Moritella profunda. So we think that the decrease in activity is due to this strong but very rigid hydrogen bond. But in Moritella profunda, you have the rise just like you do in the wild type E. coli, but it turns over. But actually, if you remember, Moritella DHFR unfolds at 0.7 kilobar. So we think what's happening as it goes over here is the protein is actually starting to unfold. So it's starting to pressure unfold. So that is a driving force. So the reason why you have this decay at high pressures is for two completely different reasons. So I showed you the case where it was the melting pressure didn't make a difference. That's Moritella profunda DHFR. But actually, if you look within the same genus, within Moritella, there are some DHFR that are found at the bottom of the Mariana Trench. So they experience pressures close to 1,000 times atmospheric pressure. I say PG is a 800 bar because its optimum growth is the 800, but it's actually found in the bottom of the Mariana Trench. So we think you would think it have to adapt so that it doesn't unfold. We don't know for sure what the melting pressure is, but since it's active there, we assume it must be doing something. We can look at that the glutamic acid. It doesn't change to anything. It's already this glutamic acid. But what we see, there are 155 or 160 residues about. Out of that, there are 3 sequence changes. And the one that we think is important is the cysteine at 103 goes to a tyrosine in the Moritella noci. And what happens in MPDHFR in its simulations is that this cysteine hydrogen bonds to isoleucine 99, which are both within the same helix. But what happens in MYDHFR is that the tyrosine actually hydrogen bonds to a residue that's in another helix. So what we think it's doing is it's increasing the stability by attaching those 2 helices so you can't melt. Okay. Okay. So my conclusions are, so I think the material properties of an enzyme are important for adaptation to TMB. So these are adaptations regarding the protein matrix around the active site. There can be active site mutations that actually, change. You can change the charged to a not charged or whatever. But there are these adaptations which actually are changing the properties of the matrix. They're not changing the properties of the active site per se, but the matrix. And so these kinds of things that you have to worry about are increasing the temperature because you have to make sure the thing doesn't unfold. That's the greatest stressor. Decreasing the temperature, either to freezing, you're going to change the flexibility, and increasing the pressure requires compressibility. But like I said before, these are less important stressors because you just end up with an inefficient enzyme. So the direction of evolution, whether you're going 2 away from a stressor is important in understanding the types of adaptations that you're going to have. And sort of in regard to that first question I started talking about is like what the protein matrix is about. So one of the things I've tried to show you is that nature is actually worrying not only about the stability of the protein, the scaffold, but its flexibility. So it's actually interested in not just the scaffold as a scaffold per se, but what I like to think of a lot of proteins as is they're not just a static scaffold, they're like a machine. So when you go through the catalytic cycle of DHFR, it goes through a series of binding and releasing the covector and the substrate and the product. And at each step of the way, there's a slight conformational change. And if you affect that balance, which you can by the temperature and pressure, what you're doing is you're affecting its ability to act as a machine. And I think that is one of the reasons that we have proteins is because they have this ability to have more flexibility, and that by that I mean dynamic flexibility to go through these conformational changes. Okay, so I just wanted to acknowledge people in my group. Also, I showed the work of 2 people who've left and gone on elsewhere. My collaborators, my funding, and my computational resources. Okay, thank you.
All right, thank you so much for that great talk. And we have time for a few questions.
Thank you so much for your talk. I was wondering, you kind of alluded to it at the end. Are there cases where, say, a protein going from a low pressure system to a high pressure system where it's such that the protein totally changes its function, it's no longer in its original purpose? And if that were the case, the proteins that you maybe look at where they do have mutations that allow them to maintain their original function, would those proteins then just be more fundamental to the network and more important than, say, a protein that changes its function?
Okay, so one thing, I have not done exhaustive studies. There may be some proteins that have, I'm sure that especially when you start going between species, there are obviously proteins that change function based on mutations. I don't know of any protein, as far as I know, no protein has completely changed function based on a single mutation, but there might be examples, but I really don't know. But we actually are, what we've been looking at is ones that maintain the same function. So that, because we're concentrating on that, I haven't really looked for mutations that change function.
Thank you so much.
Thank you very much for the very interesting presentation. It's kind of a technical question, but in the presentation you showed a graph of pressure versus activity and the 27DE exchange changed the pressure dependence.
So
you showed a graph with pressure on the x-axis and y-axis is activity, and you say D27E mutation changes pressure dependence.
Uh-huh.
And I was wondering, is that computation result? I was wondering, how did you do that?
Those were actually experimental data.
Okay.
I'm sorry, I was rushing a little bit, but that was all from experiment.
Okay. I see. Thank you.
Great talk. Thanks for giving it. I had a question about, have you looked at the bi-stacking and stacking interactions, and do they act in a similar way as hydrogen bonds?
Yeah. So, are you finished with it?
Yeah.
So I was being kind of loose, and I just said hydrogen bonds. There are obviously a lot of other interactions that are important besides just hydrogen bonds. There are hydrophobic interactions, there's pi-pi stacking. I was just using it as a catch-all phrase to describe interactions. Actually, some of them get difficult, like hydrophobic interactions. But one of the things about why I talk about hydrogen bonds is they're specific. And so, so yes, everything else is important too, and they can contribute to the effects.
Great, thanks.
Thank you for this presentation. So you showed the hydrogen bond frequency with temperature and pressure changing. So I wonder how is that affect to molecular vibration? I think if temperature and pressure increase, molecular vibration energy may increase because vibration frequency may increase and bond length is maybe shorter.
Right.
Yeah. So I think the molecular vibration energy may increase.
Yeah, so with temperature, of course, the vibrational energy increases because you have just more kinetic energy. And that's why you tend to break. But with the thing about pressure is you would think it might strengthen some bonds because you shorten the bond length, but you also torque it.
Yeah, pressing molecule and the frequency of bond type of water is increased and with.
Yeah, and it should vibrate fast. And the other thing is that there's another difference that I didn't really talk about between pressure and temperature. So temperature is, it follows a Boltzmann distribution. So it distributes all over the protein. But pressure, so like if you look at what happens with a change in pressure, what minimizes the free energy is a reduction of volume as you increase the pressure. And when you think about where cavities are in a protein, they're not distributed randomly over the protein. They're different in different spots. So pressure, it breaks some bonds and it increases the strength of other bonds. It's not as uniform. If you look at something like water, it actually breaks bonds at lower pressures and it,
I see. Thank you.
But that's a good point. I mean, you could look for specific changes in the vibration.
Let's thank our first speaker one more time.